y hat or f hat of x star. So there's lots of possible goals that you can have given this very, very broad context. But three that'll help motivate what I'm going to talk about. So given some point where you want to predict, you might actually just want to make a prediction, right? That might be the only goal, is to generate predictions. More commonly in statistics, you might want to do things like determine the actual form of f. So what does that relationship actually look like? And then even more commonly, what you want to do is say, well, what's the impact of one of those features on the response? Right? So if my response was, say, miles per gallon of a given car, and I record things like the weight of the car, the engine size, the brand, things like that, and I want to say, well, what's the impact of engine size on miles per gallon? I want to be able to do this on this sort of scale where I can analyze what the actual impact is of any given sort of subset of those predictors or features. Okay, and so this is how traditionally you would set up this sort of problem in statistics. You would start by saying, okay, suppose that we can define that relationship f up to some finite number of unknown parameters beta. And so we'll use the data, then given a sample of size n, we'll use the data to estimate the parameters in that model. So we'll form these estimates beta hat, and we'll use that to get f hat. Okay, so this is just one example of that. So we've got this function here, f, and this is a function of the parameters beta and also the predictors, x. And this is just a linear model. Probably a lot of you may have seen that, but this is really nice and interpretable, right? This is the advantage of this sort of setup, is that everything's laid out in front of me. I know what's going on. The model makes sense. I understand sort of what the impact is, right? If I want to say, you know, what's the impact of x1, I have this beta 1 coefficient out front. So this isn't, of course, the only kind of model that you could use, but this kind of approach gives you the ability to do things like that. Okay? So that's the advantage. And the disadvantage to this is a quote that statisticians are probably a little bit sick of hearing. But old quote by George Bloch said, all models are wrong, some models are useful. So what this means in this context is that if we assume, we make this general assumption up front that we can define f up to this unknown set of parameters beta, if we don't specify that model exactly right, then how much do we really trust the inference and the results that we're getting? Okay? So another more subtle disadvantage to that is that what if we just really have no idea how to define that model f? Right? So for a long time, statisticians have sort of gotten around this problem by saying, well, you know, no models are perfect, right? So we'll find something close, we'll find something that we think is reasonably representative, and we'll sort of chug our way along. But here's an example of a case where that's particularly difficult, and this was actually one of the original motivating examples that sort of got the ball rolling on what we now think of as sort of modern day statistical learning or machine learning. So given an aerial photograph of a ship, can we just predict what kind of ship is in the photograph? Right? It's a fairly straightforward problem. So here's two examples of two different kinds of ships. So in this context, the response then is the kind of ship. That's what we want to predict or model. So what does the data look like? Well, if we think of this as being in grayscale, we sort of think of defining a grid on each of these photographs. And if we think of this as being, for example, a 16 by 16 grid, then we've got 256 grid values, which we think of as pixels. And then the values that those predictors take depend on how light or dark that particular area of the photo is. Makes sense? So given these 256 predictors or features, then how do we define that relationship F? Something that's really difficult to do. Okay, so how does machine learning try to get around this? I have to be a bit intentionally vague here, but the basic idea is that, so the terminology of machine learning is training set instead of sample, but they refer to the same thing. So given the training set size n, we'll just sort of go through the data and we'll find a bunch of patterns in the features that are most associated with certain patterns in the response. Okay? So once we've found a bunch of these patterns, we'll stitch them all back together in such a way to form some estimate of f hat. Okay? So the way that we look for those patterns, the way that we find the patterns, the way that we stitch those patterns back together is sort of what differentiates between different kinds of machine learning algorithms. Okay? So the advantage to this is that we're really making almost no assumptions on what the data looks like. In a statistical sense, this is sort of fully non-parametric. And what usually happens is that given a lot of data, the f hat that we end up with usually looks a lot like that original f. So if we only want to do predictions, this is really, really good. Right? We have something that looks a lot like the underlying relationship. The disadvantage is that this is really difficult to interpret. So now we're sort of on the opposite end of the spectrum of traditional statistics. So traditionally in statistics, you say we've got this model and we understand what's going on, we estimate the parameters, everything's all well and good, except what if we don't know, if that model is actually correct. And now we're on the opposite end of the spectrum saying we're going to get a model that we know is really close, but it might be really, really difficult to interpret. And just to sort of drive home this point, a lot of times what this means is that you can't even write these things down in some sort of algebraically compact form. So you store the results in some kind of computer or code or algorithm or whatever you're using, and it really can't even give you some nice closed form from what that f hat looks like. Okay. So here's one such example of this. I should say up front that this is a really, really, really quick overview of something that could probably have an entire lecture devoted to it. So don't take it too harshly if this doesn't come across as all that intuitive. But so this is part of this general classification and regression tree or CART framework that was developed in the mid-'80s. It's still very popular now. And the basic idea here is that given the feature space, so in this example I just have an x1 and x2, so two features or two predictors. So given this feature space, I'm just going to partition this up into areas where the responses are much similar. Okay? And once I've done that, once I sort of finish splitting up the space, I'm just going to take all of the data that were in each of those spaces and record the overall average. And the advantage to doing this is that I can write this as this binary decision tree that's over here on the right, and then when I go to make a prediction, I just see which of these regions that point where I want to predict falls into, and I predict as whatever average I had from before. Okay? So the end result of this is that you get some piecewise constant estimate of f hat. That's a very overly vague description of what's really going on here. But any questions up to you? All right, so typically in practice what you do is that you wouldn't just build a single tree. You wouldn't just do this one time. What you come across more in practice is based on bootstrapping. So if you don't know what bootstrapping is where we have the original sample and we draw another sample from that sample. It's the same size of the original sample, but we take it with replacement so that we get back something that looks a little bit different. Right, if we took it with replacement, we would get back the exact same sample. So we take it with replacement, we do this a bunch of times, and we do whatever we were going to do on the original data set with each one of those bootstrap replicates. And this is sort of the first obvious extension of this. It's called bagging or bootstrap aggregating. So we say we'll take B bootstrap samples of the original training set, or sample. We'll build a regression tree with each one of those. And when we want to make a prediction, we'll use each one of those trees to get a prediction, and we'll take our final prediction to be the average over all of those predictions. Makes sense? So this is what I have written here. So if we take B bootstrap replicates, this T sub x star is just what I'm using as a function to denote the tree that sort of maps from the training set to the prediction at x star. And so we do that B times for each one of those, and we average over them. And then random forests are sort of the next extension of this. And I won't get too deep into this other than to say that with bagging, we assume that each tree is built in exactly the same fashion. So we're doing the same sorts of things with each one of those bootstrap samples. And with random forest, we add in this extra little bit of randomness here, which I'm just denoting here by omega sub I. And the intuition behind that is that when you do bagging, most of the trees are going to find most of the same patterns. Okay, so the idea is that you might get an estimate that's a little bit more stable, but probably doesn't improve predictions all that much. And the idea with random forest is to say, if I sort of add in a little bit of randomness, then hopefully different trees in the ensemble are going to find different smaller patterns, so that when I look at them overall, I can sort of get all of the big patterns that all the trees find, plus all of the little patterns that I sort of got by adding in that randomness. Okay. And random forests, to this day, are still considered sort of the best, what we call off-the-shelf methods, meaning that they're robust to a variety of data sets, and you don't have to do a lot of fiddling with them to get really good predictions. Okay, so there's a lot of like these online predictive competitions, things like Kaggle.com. Ever heard of that? But what you'll find in a lot of those competitions is that the people that post the competitions, they typically will give you a random forest model off the top and say, this is how good you can do with a random forest right away. And that's really not a trivial thing to beat. In most of those competitions, the base random forest model that you use without thinking about anything at all is typically in the top 10 or 15% of all the submissions. Okay. All right, so just a quick recap. So traditional statistical models puts everything out in front of us, makes everything intuitive. It allows us to do inference when we put certain assumptions on everything. But we worry about how wrong they might be if we misspecified the model. And then learning algorithms allow us to fit everything well, but they might be really, really difficult to analyze. Okay? And so what we want to do, what the goal of this is really to do, is to get formal statistical inference in the context of machine learning. So in particular, we want to get confidence intervals for predictions. And what this means in practice is that if I've got some point x star where I want to predict, and then I think of getting a new data set and building a new learning algorithm or a new ensemble, how different might I expect that new prediction to be? And then we have two kinds of hypothesis testing, which I'll talk a little bit about more as I go through the talk. But so the first is a test just for feature significance. So if I think of breaking up all of those features into two groups, call them x1 and x2, I want to say, could I write that relationship as just a function of the features that are in x1? Okay, so do the features in x2 actually matter at all? And then a test for feature additivity. So this gets more into the structure of what f actually looks like. But again, given the same setup, given two groups of these features, x1 and x2, we say, could I write it as an additive function of those two? Right? So to scientists, what this means in practice is that if you can write it like this, then that means that I can change the levels of all the features that are in x2 without affecting how x1 affects the response.
You don't want cancel effect, right? Obviously, for such an addition. If something go up, something go down, cancel each other, you will actually diminish the distinguish. You can distinguish things, right?
In an additive model?
So you want to add two features, right? Each feature will show some similarity of the data. And if you add them, you don't want one go up, one go down, you have those cancel effect. The simple-minded idea is that you want two features, they superimpose on each other, you will even show stronger evidence that they are similar, right?
Sort of. I mean, the real
It's a correlation, right? If the correlation is negative,
Sure,
then you
sure.
cancel, then it is bad, right? When you add two features.
Yeah.
Right.
In
So there's some restriction how you want to add the two things to add. Without much statistics, just think about the cancel effect you don't want.
Yeah, I mean, if you were doing traditional statistics, yeah. In the context of machine learning, you sort of, all of that sort of gets built into the learning algorithm in some sense. But I know the point. The real point is just to say, as I go across the feature space, is the effect of one of the variables changing with the levels of the others? Or could I change them without affecting that feature space? Okay. All right, so